nanohub.org.
Online simulation, and more for nanotechnology.
Good morning from my side, and welcome to this seminar. So the title that I chose for my talk was about it's about the overarching goal of the system being like the investigating the dynamics of driven dissipative system in the strong interaction limits and in the vicinity of non-local interaction. So the phase transition is not something new. It's perhaps some of the phenomena that we've been encountering over and over during our life. And the very classical definition of phase transition is just a substantial qualitative change of the equilibrium properties. Though some of them are kind of vague, like the substantial or qualitative, but at least equilibrium is something that it has a very well-defined meaning. It's a thermodynamic and it's in a closed conservative system. And more mathematical notion of the critical point to the nth order is basically where we cannot have the nth order derivative. And that's where the phase transition is happening. But then what's about the quantum phase transition? So we know that we have like different fluctuations in our system. If we can go to the absolute zero, where the thermal fluctuations are zero, then all the remaining fluctuations will be due to the quantum, and then the driving fact for the phase transition will be the quantum fluctuations. And that's what we talk about, quantum phase transitions. And this is a pretty well-known textbook example of a quantum phase transition. So when we are above zero, then we are talking about the classical phase transition. But then when we are approaching the zero temperature, then all the phase transition is dominated by quantum fluctuations. So we have the quantum critical point and quantum phase transition. Of course, absolute zero is not something that we can achieve experimentally. So we are talking about some approximation approaching this zero limit when the thermal fluctuations can be suppressed. And that's what we are talking about quantum phase transition. That's this region. And of course, this has been investigated a lot in the past. Here I'm giving some examples from cold atom systems, but of course, the quantum phase transition has been around for a long time before that, especially with liquid helium, some of the interesting, mysterious systems, which it still is. But then here, since we are focusing more on the atomic side, I would like to give you some examples from the atomic phase transition. Of course, at the early of this century, we had the Bose-Einstein condensation. And then if we have the contact interaction, then we could have the phonon modes and then superfluid and appearance of the vortex nucleation. And within the last 2 years, there's been an interesting body of work about super solidity when we have, in addition to the S-wave scattering, we could also have the non-local scattering and interaction competing with that contact interaction, and leads to appearance of a new phase of matter or a new type of matter called supersolid. So then the natural question that we can ask is that, can we have quantum phase transition for photons? That seems to be kind of quite natural question, because photons are basically like the founding fathers of quantum mechanics, if you wish. So then we can say that, can we observe some of them only in an ensemble of photons? The answer is not very clear, although we could think about just lasers or photon BECs, but let's delineate some of the differences between the photons and other material systems. First, photons do not interact, or they barely interact. So there is a lack of direct many-body effects, and I would kind of discuss about this direct during my talk. And then the other main difference between photonic systems in opposed to matter system is that all these photons, they are kind of open system, the photonic system. So they're driven dissipative. So if you think about the initial criteria that I told you about the limit of t going to zero, basically at the limit of t being zero, there is no photon. So that's one main distinction that we have with material system. In other words, chemical potential for photons is zero. And we have to do something about it. But there is some way to overcome some of these deficiencies. One is to hybridize photons with matter degrees of freedom to get polaritons. And of course, we can utilize the matter-matter interaction to induce the interaction between polaritons. And since we want to still have the major part coming from photons, you can imagine that the interaction between the polaritons are typically weak. But anyways, this has been kind of quite active branch in AMO physics. And there have been a lot of interesting study, for example, hybridizing the photons with excitons, hybridizing them with Rydberg atoms. And then the very recent study from Atachi Mamoglu was quite interesting, basically proposing to use polarons, which is just like quantum emitters in 2D materials, and hybridizing them with polariton. And they are showing like orders of magnitude enhancement in the interaction. But still, compared to the atomic system, we are far away. So to be more judicious in choosing the material system, let's look at the available options out there and see that what we can do to really push the limit of interaction between the photons further. Here I'm summarizing at least like 4 different material systems based on their interaction, and I'm discerning between the weak interaction and the strong interaction based on the number of atoms that we can say we can have in a sphere around with basically S-wave scattering length. So if I have less than 1 atom close in the scattering length, I would call it a weak interaction, and if I have more than 1, I would call it a strong interaction. And we could start from the case, which is just the neutral atoms. It could be that even if we do not have any interaction between the neutral atoms, we could still go to the Bose-Einstein condensation, of course. The very small S-wave scattering between the atoms gives us the interesting phenomena, appearance of the phonon modes, the superfluid, and it's been the workhorse for a lot of studies on atom optics. A lot of people started working with dipolar atoms. The lanthanide started with chromium, and then nowadays with dysprosium and erbium. People have demonstrated additional effect in these systems when we have the interaction between the magnetic dipoles. And then on top of the superfluid range, now by changing the interaction, basically the ratio of interaction between the dipole-dipole interaction and then the S-wave scattering interaction, contact interaction, one could have the super solid and long range interaction. And more interestingly, it's kind of anisotropic interaction. That's a pretty active field of research these days. So I would kind of refer you to a very interesting recent talk from Francesca Ferlino from Innsbruck about these activities in his group, and my colleague Tim Langen's talk in a long-range workshop in a couple of weeks. But then these are about the magnetic dipole. So natural question is that can we have like this interaction between electric dipole? They are stronger. And the answer is yes. That's where we talk about the dipolar molecules. But remember that the dipolar molecules, they are not that easy to tame in opposed to the atomic systems. Their Frank-Conan factor is not diagonal. So the branching ratio is not 1. And that basically makes them a bit hard to be laser cooled. But anyways, a lot of people are working on that, and the future for the dipolar molecule is bright as well. But then what I'm kind of more fascinated about, and what Tillman tried to kind of push me in that direction, was about the Rydberg atoms. They are quite fascinating. At least we can think about the most interesting or highly interacting systems so far. They are so strong that one Rydberg atom can blockade its adjacent Rydberg atom from being excited. And I'm not going to talk about the physics of these interesting species. There are very interesting solid body of work out there, so I would refer you to a lot of theoretical and experimental work in this realm. But I would be kind of quite happy to discuss further at the end of my talk. The platform that we were thinking, just hybridizing the Rydberg EIT with optical cavity. And the idea is rather straightforward. We know that with Rydberg EIT, we have quite large nonlinearity. Basically, if I have this control photon, I can substantially control the effect of basically the behavior of the lower transition. I can make this one transparent or opaque. So this is quite strong nonlinearity. And on the other hand, we are talking about photons. So I need something to control the single particle dynamics. And that's where the multimode optical resonators come to the picture. And then now if I put them together, combine them, I get cavity Rydberg polaritons. So these are like, in terms of polaritons, that's another new type of hybrid system. But then they have the pretty interesting property that they could allow us to explore the driven dissipative phase of the system, that they have long interaction and they are not local. For more interesting work, the experimental work, I would recommend just looking John Simon's work at U Chicago, where basically he's using these entities for exploring many body physics of photonic systems, for example, like exploring the Landau level and Landau physics. But what we are interested in utilizing Rydberg polariton is mainly for exploring the phase transitions and quantum phase transitions in driven dissipative systems. So let's explore, let's be more concrete. The system of our investigation was a multimode cavity. Here I'm just showing a typical spherical cavity. Since we are talking about the spherical one, it has the azimuthal symmetry, so I can basically divide the quantum numbers to the radial and azimuthal one. So each pair for each state basically shows the radial quantum number and azimuthal quantum number. And here, for example, you can see some of the highlighting cases, the ground state, for example, the first excited state, second excited states, and so on and so forth. And the system is open, of course, as already advertised. So each level is kind of interacting with the bath and decaying with a decay rate of gamma. And then we have to pump the system to reach a long time limit. And this is a coherent pump, for example, in our case, pumping another level in this cavity. And another interesting feature, for example, for when it comes to the optical system, is that by virtue of changing the spatial profile of this pump, we could address different modes with different weights. But let's be more concrete. So the conserved part, or the Hamiltonian of the system, it has a photonic part, AM being the annihilation operator of each cavity mode. To the first order, I have two-body interaction between any two modes in the system. And then I have a coherent drive. In our case, for the results that I'm showing, we assumed a coherent drive exciting only one of the modes at frequency omega p. And then the system is open, assuming a Markovian dynamics and interaction with the bath. We could basically study only the reduced density matrix of the cavity, and the effect of the interaction with the bath is all dumped into this dissipator. So then the dynamics of a density matrix is given by the super operator coming from the conserved dynamics and the limit. As you can see, the size of the problem drastically grows. So if I have n cavity mode and the truncation number for the Hilbert space for each mode is m, so it grows pretty quickly. And just to also kind of make the problem more dramatic, I would like to remind you that in opposed to the closed system, we have now a lot more parameters. We have like a pumping rate, we have the pumping frequency, and we have the decay rate. So that's what actually makes the physics of driven dissipative system very naive compared to their conserved dynamics, because the phase space is quite large and then a lot of free parameters are there. So, but okay, what's the plan of attack? Of course, the simplest approach is mean field, but as I already told you, that's the whole point of pushing to this limit, to be away from the mean field. But mean field is our first strategy just to get an idea about the system. But then it has a caveat. In opposed to the closed system, where we are sure that there is a thermodynamic and steady state limit, we do not know a priori our driven system has any long time limit. So we'd better have another alternative approach more precisely to check and falsify our mean field results. But anyways, let's just kind of move ahead and compare these two methods together. So For the mean field, we can basically from the super operator, we can find the equations of motion for AM, which basically gives us the Heisenberg-Langevin equation. And the assumption for the mean field is kind of rather trivial. We have the scalar mean value and we have the operators. And to the first order, we can simplify the dynamics for the equations of motion for B. And so for a lot of you kind of working in this mean field behavior and then the elementary excitations, this M is simply what we know as Bogolubov matrix. So all the spectral features, the interaction, the pumping, everything is dumped into this M. And then this is kind of quite helpful that way, because from this we can calculate the covariance matrix and the first order correlation. That's the best that we can do with the mean field theory. But then what about the alternative approach? And what we found quite helpful for the dynamics of the open system is the phase space approaches. And here in particular, I'm focusing on the Wigner function, but the idea for all of them is kind of quite similar, either being like the Q function, P function, Husimi Q, or any other function that we want to think about is one-to-one mapping between the density matrix and analytic function. And then, for example, for the Wigner function, that's basically related to the Fourier transform of the density matrix and kind of expressing that in terms of the phase space variables, i.e. position and momentum. So now if I kind of put this mapping into the super operator, it's kind of straightforward to show that the equations of motion for this W, the quasi-probability function, is satisfying this type of PDE. If I do not have these third order derivatives, so you can recognize there is some terms related to the drift, and this is like some diffusion type dynamics. For the start, since this is kind of related to the third order of a probability and also has the interaction, which typically is assumed to be small, let's just omit that and we'll kind of compare that with more exact full density matrix calculation to see how valid this approximation is. But then the benefit is that if I drop this third order derivative and I get the truncated Wigner, now I have, if you kind of only focus on this part, this is really the Fokker-Planck type equation, just describing any Brownian motion or any random noise. And the benefit is that there is one-to-one mapping using the Ito calculus from the Fokker-Planck to the ST, the stochastic differential equation, and the STs are rather easy to solve. And we can really average over millions of trajectories and then get the quantum mechanical properties of the system pretty efficiently. Let's just start from the first case, which is the simplest things that come to mind, the single mode cavity. And we want to explore its phase diagram and also lay the foundation and prepare the stage for the multimode case. To highlight that how the different parameters of the system are kind of important, let's assume that we have the repulsive interaction. So I have a level, I'm using a coherent pump, and it has some certain detuning from this energy level, and it has a decay to the bath. Here, this detuning either being on the red or the blue side of this energy level could have detrimental effect. Let's assume that this is a red detuned laser. So the energy of laser is here. Since the interaction is repulsive, as I put more and more photons into this cavity level, the separation between the energy of the cavity mode and then the laser increases, so the detuning is monotonically increasing. This seems to be rather trivial side. On the other hand, if this detuning is negative, so the excitation is on the blue side, then if I put more particles, the energy of this level increases. And then at some point it becomes degenerate with the laser, and it passes if I put more particles, and then it follows the same trivial behavior that I told you. So it seems that depending on this detuning, we can really push the system to two trivial and non-trivial range. So let's be more explicit. If now the free parameters of the system, and I have to say that here I normalize everything to this decay rate just to reduce one of these free parameters, I could have either this delta naught being like the detuning of the coherent laser or the interaction. So what we could see is that for detuning, as already advertised, for positive detuning, nothing is happening. So the number of stable solution is 1. So there is one long lifetime behavior or limit, and there is just a unique solution for that. But then for the negative detuning, there is a region that we have 2 solutions. So there is a region of bistability. And this boundary is sharp. So I would kind of delineate that further. But this is kind of, we'll see it's like a first order phase transition. The same we could see for the interaction. So if the interaction is weak, so we are in the limit of mean field, or let's say nonlinear optics. So a lot of phenomena that we are familiar, for example, like kernel linearity or like the OPO physics is kind of happening here. But then when it comes to the strong interaction, then you'll see that we could get, again, the phase transition to have bistable solution. So in a nutshell, non-monotonic behavior leads to multi-stability. But then this is a single mode cavity. We want to see that what does the bistability mean quantum mechanically. Excuse me, maybe I can check the chat. There was a question here. Or maybe I can go back to that later. We want to say, we want to understand what does this bistability mean? And if that's something that the full quantum mechanical calculation also suggests that. So to compare the different solutions that we have or different behaviors, let's check the number of photons in a cavity as are observable as a function of coherent pumping rate. So the mean field solution, where basically we get all those nonlinear optics behavior, is the one highlighted with the black dots. And as you can see, indeed, there is a region. So that I have two distinct solutions. So that's the region of bistability, and they are kind of gapped. They are separated by some finite gap here. But then the full density matrix calculation, the DM, or the stochastic differential equation, both of them are kind of implying a continuous behavior, no phase jump. And the interesting thing is that away from this bistable region, all three solutions agree pretty well. And within this bistability is something that quantum mechanical solutions, including all the quantum noise, does not imply two distinct branches. And then also I would like to highlight the pretty well agreement between the full density matrix calculation and SDE. So basically that third order term that we dropped seems to be really not very problematic, at least in this range. But what does this kind of, if mean field has any truth in that, we should see something even full quantum mechanically is happening. So the other thing that we could here explore is the population of the number state. And that would help us because it tells us that what kind of quantum field we get inside the cavity. So if you look at the distribution of the number state at this B point where the pumping rate is pretty low, we'll see that it's kind of quiet. It's reminiscent of the thermal small coherent state, which actually makes sense. This is kind of where the pumping rate is low. So we have few numbers in the atom. The self interaction is low. So it is, and we are pumping the system with a coherent state. So it's kind of close to a coherent state. And since the number of photons are small, there is no distinction between the coherent state and thermal state visually, unless there is like a change in the second correlation. On the other hand, when we go to the B, for the point which is here at C, in the region of bistability, the mean field suggests two solutions. And you'll see that here, the distribution is like two-peaked. If you look at this one, there is this distribution, and there's another one. And then if you go far away in the regime, far away in the pump, regime D, we have a super Poissonian distribution. So P changes its behavior from coherent to super Poissonian. Also, if you look at the second order correlation, the G2, which it would be helpful because here where we have that's basically like the quantum mechanical observable that we could see if anything is happening here, and you'll see that G2 peaks at the region of bistability. So indeed, it seems that something is happening. But then how we can, what is that one is related to? Is this some kind of jumping, tunneling? So for that, I'm kind of a visual person, so I would like to see the phase space distribution. That's helpful. So there's, for each one, I'm plotting the Wigner function distribution in the position and momentum space. So when the pumping rate is low, so you'll see that the distribution is kind of rather circular, like a coherent state or isotropic. And there's a very small offset from the center. So it's not thermal, but that's a kind of very small coherent state. On the other hand, when we are in the region of bistability, you'll see that the Wigner function distribution is double peaked. Here it was also implied by this distribution, but it's kind of much clearer here. So we have one state here and there is another lobe here and they are connected. So that's some hint of tunneling or jumping which is happening here. And then interestingly, far away from the bistability deep into this region, you'll see that there is a non-Gaussian state appearing and it's partially squeezed. And I'll get back to this squeezing during my talk. So again, we'll see the same trend as I already advertised in the Wigner function distribution as well. But when we were talking about this kind of tunneling or jumping, the best way that we can explore it is via the, basically just looking at the quantum jumps. Since we are just solving the SDE, we can really use the quantum Monte Carlo just to see that how the quantum trajectories vary in the phase space. And the benefit is that we can see that if there is any signature of two distinct states that we have quantum jump between. So when the pumping rate is low and we are in the unique solution limit, you'll see that all trajectories as a function of time, they are all clustered around one solution. And interestingly, this is the mean field solution. But if we go to the bistable region, you'll see that we have the quantum Monte Carlo suggests two distinct clustering around two distinct values. And these two, as you might guess, this is the values predicted by mean field. And then finally, again, if you go to the large values, the quantum Monte Carlo seems to be fluctuating around one single value, which is, again, the mean field value. So indeed, it seems that when we look at different trajectories in the phase space, we indeed see the signatures of the mean field values, which is kind of associated by fast tunneling or jumping. So there is, like, you can think that in the phase space, we have two attractors and they are mean field values. And then there is a tunneling from one well to the other one mediated by quantum fluctuations. And if now you might say that, okay, we know from our nonlinear optics freshman physics, there is bistability. So where is that bistability? And the answer is kind of rather intuitive. When we are thinking about the weak interaction, basically the barrier between two different solutions that we have is quite high, that the tunneling rate is pretty low. So that's the reason that if you, within the reasonable time frame that you are doing the experiment, if we observe the system, it really seems that it's kind of really jumping between two distinct values. And that's why we see the bistability. On the other hand, if you keep increasing the interaction, the barrier between these two attractors decreases, so we can see constant jump between these two values. Just to show you that how the Wigner function evolves in time, which is kind of quite insightful, you see that all of them starts from a thermal distribution, and then the small value case is kind of really stays around that value, while for the one which is jumping, you'll see that the distribution starts to spread to two values. And the interesting thing for the ultimate largest value is that really it evolves and it kind of moves toward that non-Gaussian distribution that we already talked about. Okay, so far so good. It seems that, okay, we kind of understand to some extent the behavior of a single mode system, but then the problem becomes much more interesting now if we have the intermodal scattering by virtue of having more modes in the cavity. And that's something that we can easily do that in the photonic systems. We can basically change the radius of curvature or the cavity length, and we can introduce more modes and then have the intermodal scattering. So for the, again, the scenario is kind of extended version of what we discussed. We have one pumped mode and we have the side modes. So we can imagine two different scenarios here. Either the cavity being harmonic. So the second mode is basically just the average, really in between the first mode and the third mode. I call it like the harmonic cavity, and that's really like the condition. And then if you look at the phase diagram, this is quite similar to what we already had for the single mode case, with the caveat of having another, this kind of red region I kind of highlighted with C, which basically is the region that we have three different solutions. So we have thrice stability region here. On the other hand, if you look at the unharmonic cavity, which there is the one that there is no kind of energy balance at the beginning, then we only have the single mode solution all the time. And this solution is kind of, as you can see from the, the difference between these two values, is a continuous phase transition. So it's a second order phase transition. Let's be more clear. For example, if I park my detuning somewhere here and change the pumping rate, what we could see for the harmonic cavity case is that there is the mean field highlighted with these black dots is basically for the first mode, for the unpumped mode, has no value. It suddenly has, there is a finite region where it has value, and then it goes to zero again. Similarly, for the second mode, you can see that the same behavior for having the bistability. Now there is an additional region, which is the third stable branch of the pumped mode. And the interesting thing, again, is just the main distinction of the full solution, the density matrix calculation, and again, the SDE from the mean field solutions. It's always a continuous branch, and we always have solution. And that's not really surprising when we think about it, because these are driven by quantum fluctuations. So the quantum fluctuations are always there. As soon as I have any particle in the second mode, because of the fluctuation, I start populating the other levels. But the interesting thing is that the highest slope or the highest rate is coincides pretty well with the region that I have non-zero values via the mean field. What happens for the harmonic case? You'll see that, again, that's the same. For example, if I am somewhere here at this detuning, and I keep increasing the pumping rate, so the branch increases monotonically, I do not have any photons in the unpumped mode. And then suddenly there is a kink and phase transition here happening. So I populate the unpumped mode, and there is a finite region, and again, it's zero. And as you can see, this is like a continuous transition. That's a second order phase transition, which is happening here. Again, the behavior from the full solution, the mean field and density matrix calculation, is kind of different. But again, I'm kind of highlighting that the highest, the region of largest slope is coinciding with this mean field behavior, which there is kind of more into that, but I don't want to go into the detail, but we can discuss later. That this is basically like the signature of the mean field phase transition. But then it's all about the long time behavior. You may ask, okay, what's about the temporal behavior? You haven't told me about the temporal behavior. And then I've already advertised from the beginning that there is no a priori knowledge that in a driven dissipative dynamics, we have a steady state or like a long time behavior. So to explore that, let's focus for both harmonic and unharmonic case on a scenario that in a region for the pumping that mean field predicts that there is macroscopically populated values in the branches. And then if I look at the variation of the mean field values as a function of time, we see something interesting. The M2 is the mode that we are pumping. So you'll see that it's not changing neither in the harmonic case or unharmonic case. It's flat. And it's kind of making sense because we are in the rotated frame of the laser. And then the variation of the pumped mode is really tied to the laser. But what about the non-pumped mode? What about the M1 and M3, for example, in our case? It seems that they have some sustainable oscillations. And this is what from our nonlinear dynamics, for example, we know that these are called limit cycle behaviors. That's basically saying that there is the long time limit of a system has a harmonics or has some beat node, which is different totally from its excitation frequency. And I think, again, just I try to connect it to our well-known knowledge from the nonlinear optics. That is the one that, for example, we can think about like the second harmonic generation, third harmonic generation, or even like parametric processes in the optical parametric oscillator cases. But all in all, what seems kind of quite interesting is the presence of this time variation. And this already tells us something about the phase freedom, because it seems that depending on where, as you can see, I'm kind of highlighting just some random interval. So if I start somewhere here or somewhere here, it seems that also like a delayed or phase lagged or phase lit, it's also a solution randomly. So it seems that there is some phase freedom for both of the cases. So let's just kind of delve into that further and see that what that one is coming from. If I go back to the Hamiltonian, you can see that I can separate it in two parts. This Hamiltonian, we all agree that it has U1 symmetry. But then when I apply a coherent pump, it breaks the U1 symmetry of the system. But it only breaks the global U1 symmetry. So the symmetry of the pumped mode is broken. But I still do not know. We have to kind of investigate it further, that if that also breaks the U1 symmetry of the side modes as well or not. But one thing that we can clearly see here is that if all the modes of the cavity are occupied, then the steady state or the long time limit does not have the symmetry of Liouvillean. So I would like to remind all of us about the interesting lesson that Londo taught us in the conserved system. When the ground state does not follow the symmetry of the Hamiltonian, then a phase transition is happening. Here we have a scenario. Our system is not conserved, so the symmetry of the operator that we are talking about is not the Hamiltonian. That's the symmetry of Liouvillean, the super operator we are talking about. But it seems that we are getting a long time behavior, which is kind of breaking the symmetry of Liouvillean. So we expect that some phase transition is happening. So I kind of use this spontaneous symmetry breaking. This is really like something for conserved dynamics, but then it's really like one-to-one analogy between what we know from the conserved dynamics and the open systems. So we have a quantum phase transition. That's really what's happening, and we have this phase transition. But then let's look at the phase freedom that we have. So we know that if operator A1, so the Hamiltonian, and of course, like the Lindblad has also the same symmetry. So that's what I'm kind of focusing on, the Hamiltonian. The Hamiltonian is symmetric under this rotation. So it seems that there is a phase freedom, which doesn't change the energy. So for the unpumped mode, it seems that I have 1 degree of freedom. What that one means, so if I look at the profile, the intensity profile out of the cavity, it means that I could have all of these spatial distributions equally with the same equal energy. Then physically means that if I do this experiment shot to shot, I could have this realization, this one, quite randomly. Just to kind of relate it again to something that we already know, this is really similar like a laser. So every time that we turn on the laser, really the phase of the laser could be different. So that's the phase freedom that we have in the laser case as well. And this is kind of happening here, but then it's not like the global phase, that's the relative phase between these two modes. So then the spatial profile would be different, but no cost of energy. So it reminds of something. So if you go back to think about like our knowledge about, again, like the symmetry breaking, we remember like the Mexican had potential. So it seems that there is one direction that if I change one of the free parameters of the system, it costs no energy. And that is important because it means that if there is a small fluctuation, my system is kind of quite free to move around us. But in the other direction, which is like in the orthogonal direction, then the system encounters a restoring force. So if it moves in one direction, it's kind of, again, pushed down to the bottom of this well. And this is like the picture that we can think of. So my system is really invariant under this change of phase. So no energy is changing. This is like the Goldstone mode. And then this is like the amplitude or the Higgs mode. So I'm changing the mode in this direction. It's kind of restoring force. It comes back at the bottom of this trap. how we can see that, what is like the quantum optical signature of that. So we can think about the heterodyne spectrum. Why is that? Because there really we can kind of measure the relative phase between the fields. So if I look at the heterodyne spectrum of the output field, which is basically like the Fourier transform of the autocorrelation function, I can see something quite interesting. So this is like the spectrum of the X quadrature, and this is for the P quadrature. And for two cases, this is the harmonic case, the delta D being 0, and this is unharmonic case. So we can see that there is a mode that it has 0 fluctuation. It is fully squeezed. And then on the other hand, I have a quadrature which is fully divergent. Now, if we kind of tie this one back and go back to the language of Goldstone mode, so this is the one, you remember the physical picture was that there is a mode that if there is like small fluctuation, it kind of rotates around, and there is like a huge uncertainty in the phase. So that's why its fluctuation diverges. On the other hand, for its conjugated variable, it's kind of suppressing all the noise, as if it's kind of dumped into this quadrature, so it's kind of fully squeezed. And this is like the Higgs mode that we are observing here. So the interesting thing is that there is an unconditionally fully squeezed mode, which is appearing here. And by unconditionally, I mean that it's not, it really is kind of coming from that phase freedom or the layout of the potential that we have. So it's not anything dependent on the other parameters of the system, which actually makes it kind of quite interesting. But then you can just kind of ask, okay, everything that we said seems to be okay, but all this description was about the field, the mean field that we talked. Is it robust? Is this Goldstone mode robust for all the quantum fluctuations that we have in a system? And that's kind of quite interesting questions, because that's really uncharted territory so far. And this is quite interesting to see that what breaks this kind of squeezing, or what is like this limit of squeezing. So to explore that, I kind of remember you that we had some Hubbard type interaction, that was this V naught. And I can just define a dimensionless parameter like n. You might already guess, which that should have something related to the number of particles in a system, but I would like kind of leave it as an independent scaling parameter. But the thing is that if I increase this n, and V naught approaches the 0 plus, or the very small value, so you see still it's kind of the interaction in the whole system is noticeable and measurable, but the interaction per particle is small. That is certainly the limit of the field description and where we had the Goldstone mode. So then what happens if I change this n parameter and explore the spectrum of the light coming out of the cavity? So because the physics is kind of quite similar for both transitions, for both type of phase transition, I only focus on the second order phase transition. And to start, I choose one point in the A phase. A phase was the region that mean field predicts nothing. And we know that quantum mechanically we have values, but mean field predicts nothing. So what we can look at is that let's keep changing this V naught. Basically, this is like a weak V naught. This is like the strong V naught. And we are looking at the spectrum of the light coming out of the cavity as a function of detuning of the laser. So what we can see is that basically there is no thermodynamic limit, or there is no asymptotic behavior. Nothing is changing by changing this interaction. And then equivalently, we could also look at like the first order correlation, which basically measures the coherence. And we see that there is no coherence is appearing here. And if you think about it, that's not really that surprising, because that was the region that mean field predicts nothing is going on. So why there should be any thermodynamic limit there? So let's go to the other interesting phase, which is this C. This is the region that mean field predicts that some macroscopic population is happening here. So I expect to see some thermodynamic behavior. And that's where the problem becomes very interesting, because when the interaction is strong, you'll see that the output spectrum is showing some signature here, let's say. And then as I keep decreasing the interaction by virtue of increasing this n, you'll see that this feature becomes sharper and sharper. And then if I also measure the first order correlation, you'll see that corresponding to that, I have pretty fast decaying correlation or coherence. And then the coherence becomes more and more long-lived as I go to the weaker interaction. So then there is an asymptotic behavior. Let's be more quantitative. So if I keep doing this study and calculate the correlation spectrum of the output field of the cavity, and then plot this gamma, the width of this as a function of this dimension less n, there is a non-trivial behavior, as you can see. So when this n is small and we are in the limit of a strong interaction, you'll see that this gamma is finite. But then at the limit of n going to the large or infinite number, this gamma asymptotically approaches zero. What about the phase space distribution? Because that was kind of a very interesting visual aid. So for the weak interaction, for the strong interaction or for the very small number somewhere here, you'll see that it has some signature of a squeezing, but it's not fully squeezed. But then as I keep increasing this number n and decreasing the interaction, you'll see that this one approaches the fully squeezed quadrature that I already advertised and is predicted by the Goldstone mode. For sake of fun, and then just with the attempt to find like a scaling law for the system, let's try to fit this approach to the end. And very interestingly, we'll see that with good confidence, we can get the 1/n scaling. So it seems that there is some, as for any kind of like phase transition or thermodynamic behavior, we have some inverse to the number of particle behavior, just inversely proportional to that. So again, just kind of saying that in words, when we approach the thermodynamic limit, the Goldstone mode appears. That's like a full squeezing and then zero line width here. And this is all this is kind of quite clear both in the output spectrum and also the field distribution. So what's next? I would like to kind of go back and just give a shout out to this gentleman, Arthur Shallow. The interesting study of Shallow basically was awarded him the Nobel Prize, but more interestingly, he taught us about some limits of the laser line width. No matter how well we are doing in our system, we cannot never make the laser line being zero. And the reason is kind of really Heisenberg uncertainty limit. There is something that limits that, but we know that if we have more photons in a laser, the line width becomes narrower, and that's really just a asymptotic behavior. And I would like to remind you, if you kind of compare n to -1 by n to -0.9 in the system. But then we were asking if that's like the coincidence happening here. But no, if we think about the laser, really like in terms of quantum phase transition, laser indeed is a driven dissipative system, and it is out of equilibrium. So then we were asking, is it like a general scaling law for quantum phase transition in open systems? This, we honestly, we do not have like a fully quite conclusive answer for that. But the very interesting thing that we found out was about this Liouvillean gap. I remind you that the whole behavior of the density matrix is just governed by a super operator Liouvillean. So then we can look at the spectrum. Instead of looking at the spectrum of a Hamiltonian as we do for the closed system, let's just look at the spectrum of a Liouvillean. And we found something quite interesting. There is a gap happening in a finite size system, and as we increase the number of particles, this gap closes. So that basically is the signature of having like bistability, because it seems that now we have two solutions. And if I have a system with like having more and more these bands touching zero, then that's like the multi-stability region which is happening. But then down the road, we were asking some kind of general questions, just kind of guide us through, and then think just ahead of us. What happens if you go beyond the contact interaction? So I already advertised Rydbergs are great because they have a strong interaction, but we don't want to forget that they also have non-local interaction, and they are kind of long range. And we've already seen a lot of interesting recent studies on super solid behavior in conserved systems. So we were asking if all of those phenomena are transferable and they are robust if we go to the driven dissipative system. The other interesting question that we were thinking of, and that was kind of along with a lot of studies that also has been done with some of the people in the audience, was going beyond two-body interaction that we have here. And then can we see something like the Efimov states happening. And then relating this kind of the whole attempt for photonic systems was for quantum information and entanglement. Can we go beyond the Gaussian states? So what I'm trying to do here at Purdue is really realizing this system in a solid state platform. So for that, I'm kind of proposing Fabry Pro cavity, where it could be like either with the solid state systems, or it could be with the fiber cavities. But then the material of choice that I'm using for this study would be cuprate oxide. These are the systems that have been shown that support the Rydberg state up to the principal number of 30. They are still far behind what we could get in atomic systems, but there is a very recent proposal and study by Thomas Pohl that I really encourage everyone to have a look if you are interested. And they were kind of exploring the perspective of 2D materials and cuprate oxides for exploring the interacting polariton systems. And of course, our goal along the lines of the predictions and the theoretical studies that we had was to explore the effect of openness on quantum phase transition, superfluidity, and supersolidity. So at the end, I would like to acknowledge the great people that I had the pleasure of working with within the last 2 years on this project and kind of really different aspects of that. Tillman for always dragging me to the Rydberg physics. Geza for always telling me that Gaussian states are boring, and Jacopo and Robert for always trying to push it in the direction that we can really measure it and observe it. And of course, thank you all for your attention. And I will be very happy to take any questions. Unfortunately, I cannot hear you, but I'm very willing to answer any question. Before I leave, I would like to, I think that we got the message from the David advertising this one, but I would like to advertise it more. This is the very interesting meeting organized this year by Tillman Fa and Chris Solomon. And we have quite interesting talks here. So if you have time and you're willing to just kind of start your day a bit earlier, I would really, really encourage to check the program and attend it. Thank you so much, and looking forward to more discussions. Okay, so there was a question from Liping Yang, if I'm not mistaken by the name. So it was asking about there is a single mode system, how phase transition can occur. That's a very interesting question. And I would like to kind of briefly answer that, and I would be happy to discuss more. One thing which is kind of, so in this driven dissipative system is happening, the phase transition, I think we had like very expert in the audience, Roy Hanai from U Chicago, that they did a very interesting study, basically relating that one to some sort of parity time symmetry breaking in this driven dissipative system, so that they have like the gain and loss at the same time. So that basically relates pretty nicely the concept of phase transition in the closed system with the open system. So what I would like to say in brief is that when we have like this coherent drive and we have the loss of the system, we could have one point which is called the exceptional point. And this exceptional point is really has the all the consequence of the phase transition which is happening. So in a short, I would say that this is the interplay between the coherent drive and the loss that you have leading to this phase transition in the single mode system. So although that's a single mode system, but please just keep in mind that that's an open system after all. And you have kind of more parameters involved here that leads to this phase transition. Okay, there was an interesting question from Alex, I believe. How much interaction will you be able to get with the COG system? That is also pretty interesting question. So first, I would like to emphasize that the figure of merit that we are talking about in this open system is the ratio of the interaction to the decoherence decay. So If you remember, the diagram that I had for the interaction of the conserved system was NA cubed. But then here we are talking about the basically V naught over gamma. That is our figure of merit. And the V naught that we will get, I think I have to talk about the MEV now. We're going to the condensed matter system and the solid state. So we can get the interaction on the order of hundreds of kilohertz. And that basically tells us that we need some limit on the cavity. So it should be like a good cavity. But this is really like the scaling that we are talking about. So if you want the absolute number, that would be hundreds of kilohertz interaction that we get with the cuprite systems. But then it means that the cavity should be a really good cavity. Do I answer your question? Please let me know if that's not the case. Okay, Chen Long is asking, you mentioned you want symmetry in the Hamiltonian. How does Lindblad term affect the symmetry? That's a very good question. So as you can see, the Lindblad is symmetric. So if the process is Markovian, so you have like the A row, A dagger always, or A dagger row. So it is always U1 symmetric, unless we talk about non-Markovian system, which is interesting per se, but that's not the thing that we are exploring here. So short answer is that the Lindblad term doesn't change anything about the symmetry.